Okay, so this is what the title says, Calc 1. This is Chapter 2.2, Study Points 11, 12, and 13. So we're going to talk about limits and numerical investigation of point discontinuity and determination of the direction of a vertical asymptote. Okay, so the first thing I want to point out is that limits is not really that complicated. What I want you to just think, if there's some function, here's x, here's f of x. A function is continuous if I can draw it without lifting my pencil. So I'm going to write that down. So, for example, there's no jumps. There's nothing like this going on, where I go along and then I jump up to here and do something like that. That would be discontinuous. And another thing it doesn't do is there's no asymptotes, like that. That would be breaking the rules. Those are the two most common discontinuities that you'll see in calculus class. But from a very simple standpoint, there's, say, a point on the x-axis. It could be 2, for example. And as you approach 2 from the right and the left, you're approaching f of 2 from above and below, or even from just one direction. So, for example, maybe this is 4, and as I approach 2 from the left, I'm approaching, I'm going up, 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 up. That means I'm going up, 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 up. Okay? And as I approach 2 from the left, I'm going down, 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 down. And I'm approaching this point on the curve. The curve is just a way of showing you which x's map to which y's. Okay, I want you to think of the function as just a magic machine, and you can think of this. You can think of, here's my function. That didn't work. It's better. So if I put in 2.1, maybe what I get out is 4.3. If I put in 2, maybe I get out 4. Maybe if I put in 1.9, I get out 3.7. Here's function, and it's a mystery. What I'm going to do is I'm going to show you a little bit of an epsilon proof to try to get this concept to sink in a little bit. So in this case, the Greek letter epsilon just means small. So if I have a function y equals x squared minus x plus 2, first of all, polynomials are continuous everywhere. So any point I pick and any epsilon I pick, it's going to work out. So this is a little bit contrived because it's too nice of an example, but that's okay. I'm going to let x equal 2 plus epsilon. So what I'm doing is I'm essentially recentering this. I'm thinking about this function. It's a relationship to 2. So think about if epsilon is 0, put 2 in here, you get 4 minus 2 plus 2. So I put in 2, I get 4 out. Okay? But let's just see what happens. This is y is equal to x squared minus x plus 2. I like to put that template in. But x is 2 plus epsilon. And if I work that out, I get 4 plus 4 epsilon plus epsilon squared minus 2 minus epsilon plus 2, which gives me 4 plus 3 epsilon plus epsilon squared. Okay? I've actually just recentered this whole parabola, but I want you to just think about the fact that as epsilon decreases to 0, y decreases to 4. Or as epsilon increases to 0, epsilon could be negative. As epsilon increases to 0, then y is going to increase to 4. And the reason why is this sign is positive here. So when I have positive epsilons in my x, I end up with positive 3 times as many epsilons in the y. And I am going to end up with epsilon squared, but that little piece isn't really going to matter. And let me show you what's going on. Let me give you some numbers that sort of explain that. Okay, so if y of 2 is 4, but y of 2 plus epsilon is this expression, let me show you what happens. Right here, I'm just letting the epsilon be something very easy to see. The epsilon is 0.1, 0.01, and 0.001. And let's see what happens to our calculations. In each case, we have a 4. And then in each case, we have a 3 times epsilon. Okay. And in each case we have an epsilon squared. And so this gives us 4.31, this gives us 4.0301, this gives us 4.003001. So the point I'm trying to make is you can just see the epsilon, the 3 epsilon is here, and this is the epsilon over here. And then over here is epsilon squared. Okay, and that structure continues. Here we have 3 epsilon, epsilon squared. 3 epsilon, epsilon squared. The baby is totally fine, by the way, just so you know. Okay, so some functions have gaps in them, but we can still play this game. Okay, so let's say, for example, we have this function that looks really ominous. But the truth is, I can go from the right and the left, and I get this whole epsilon thing coming out. But at the point itself, guess what? The whole thing breaks. So as an aside, I want you to note, this function is really just rigged to have a hole in it. So this function is a perfectly good function except for this little hole. And the way this function looks, okay, it's going to have an asymptote at x is -1, and at 0 it's going to be 1, so it's just going to look like this. And then at x is 1, it's going to have a hole, so it's going to have like a hole right there. How do I do that? I'm going to make a little hole here. So this is what this function is going to look like. But let's pretend we don't know that. Okay, so you can see you can get as close as you want to that point without causing any harm. Okay, let's pretend we didn't know that, and let's use the epsilon argument. Try x is equal to 1 plus epsilon and see what happens next. Okay, so we have limit. Now instead of x going to 1, we're going to let epsilon go to 0. And it changes this. We had x minus 1 on top. So there's x minus 1. We had x squared minus 1 on bottom, so x squared minus 1 on the bottom. So we do out a little bit of algebra. 1 minus 1 is going to give us epsilon. The bottom is going to be 1 plus 2 epsilon plus epsilon squared minus 1. Those are going to cancel, so those cancel. And you know what? You're going to factor out an epsilon on top and an epsilon on the bottom. And so the point we're making here is, since we're never going to reach epsilon being 0, epsilon is going to go to 0 but never going to be 0, we can allow ourselves to cancel out those epsilons. Okay, so this is a little sleight of hand, but you know, it's valid. And so now we can pop the epsilon in, and the answer is 1/2. So this picture I drew up here, this is actually, this point is 1, 1/2, which we knew because it's really like that function up above. Okay? All right. Okay, what about this? Let's say we don't know algebra. Let's say we have a number, or we have a function of some sort, and all we know is we put in a t value, and the computer comes back with an f value. Okay, so maybe we want to zoom in on 0. Okay, so we can think in our mind, if we had some kind of graphing facility, it would look something like this. Plus and minus 1 would be here at 0.16228. Then it's going up a little bit, and it's symmetric on both sides, and it seems to be coming in to some kind of limit here. So we're guessing here that this point is going to be 0.16 repeating, which actually turns out to be something nice. My mind's drawing a blank, but it's a really nice fraction. Anyway, it's actually 1/6. There we go. So, so we're saying, we guess that f of 0 equals 1/6 if it exists at all, because we don't know. This could be one of these functions that look like this, or it could be one of these functions that looks like this, or it could be one of these functions that look like this. Okay, all those are possibilities, but we don't really know. But all we know is what's happening to the limit on either side, and so it's approaching this spot, which could be filled in and it could be a hole. I think I talked in class about this idea of a mountain. If you're walking along here on top of the mountain, and there's a cliff there, right? This is the discontinuous surface here, but down below you might be walking around and it's continuous down below and it's continuous up front, but there's this break, okay? There's this jump discontinuity of sorts, and a point discontinuity would be equivalent to boring a hole down here in the mountain, where you drill a hole like down to the center of the earth or something, but you drill yourself a hole, and then what that would mean is that as you come towards that hole from any direction at all, come from the north, south, east, west, any direction at all, then there's a hole. But it's really obvious where the point ought to be, it just happens to be missing. Okay, so this is what's going on here. We don't know if this is some kind of bored hole or if it actually exists there. Okay, so here's a famous example. We want limit as x goes to 0 of sine x or x, and I want you to note that this sine function is odd, x is odd, and an odd over an odd is actually equal to an even function. Think about it. If you had, x to the 5th over x cubed, you'd get x squared. So it's kind of obvious that it works for polynomials, and it works for other odd and even functions as well. So we really only have to do one set of limits. The other one's going to mirror. But it looks very much just numerics. The numerics indicate that the limit goes where? To 1. Right. Okay? But the point itself doesn't exist because it's division by 0, but the limit exists. Okay, so if you zoom in on this, it's just going to look very much like a flat line. It's going to look very much, it's just got, you can see it only deflects a little bit at 1. So let's see, it looks kind of like, if here's 1 and -1, it's going to look almost like a flat line. Yeah, my computer doesn't want to cooperate. There we go. It's going to look kind of like that. This should be symmetric though. Okay, so now, what is the limit as x goes to 0 of sine pi over x? Now, this is a problem. This is sort of a setup, because now that we've done all these, most functions you can get away with just taking epsilon to be compatible with our number system, which is, let's say, 1, 0.1, 0.01, 0.001. But if we do that with this particular problem, we're going to end up in a big issue, because we're going to take the following sequence. We're going to take, with sine of x, we're going to get sine of pi. Then we're going to get sine of 10 pi. Then we're going to get sine of 100 pi. Then we're going to get sine of 1,000 pi. And this is a problem. Why? It's a problem because we're skipping over sine function. Sine really looks like this. It just goes up and down and up and down and up and down, all forever and ever and ever. But specifically, here are the zeros, right? Every time it's an integer times pi, you get a 0. So the problem with taking our sample this way is we're taking it in a certain way that hits those zeros and gives us an illusion. See, it's an illusion that the limit goes to 0, and this is not true. Okay, so let's see what in fact happens. What in fact happens is that, hold on a second. Okay, I was thinking I was going to draw this for you, and I'm like, I give up. You know what? I'm sitting here at a computer. I may as well just let Wolfram Alpha do it. You can just literally go to wolframalpha.com and type in plot sine of pi over x, and it figures out what you want. So see what's happening, that this thing, as you get closer and closer to 0, you get more and more iterations of this thing. And if you zoom far out, like over here, you see eventually you're just going to tail off. You're going to have asymptotes. But as you zoom in, these things are just getting tighter and tighter and tighter. So that's what this plot looks like. And so it's actually, you need to define this function differently. You could ask the question, what if we give f some value, maybe 0 at x equals 0? 0 would be the typical thing to pick. And then otherwise, let the function be sine of x, pi over x. Now that's a common way to close up that hole. I'm not completely happy with that. It doesn't change the fact that it keeps wiggling a lot. And you really can't do any kind of epsilon thing. It's just kind of a trick that I don't think it works very well. But anyway, something to be aware of. Okay, so next we're going to try another, well, I'm going to give you a definition. Let me write it down. I'll talk and write it at the same time. I want to define, okay, f of x is considered to be continuous at a point x equals a. I don't know why it's a, but it's always a. If f of a exists and limit of f of x equals f of a, limit as x goes to a. Okay, so a lot of books will straight out say if f of x is continuous at x equal, f of x is continuous at x equals a if, and it will say f of a exists and the limit from the right equals the limit from the left equals f of a. However, I would prefer you think separately of the definition of limits being equal and think in terms of more this, this other picture I had up here. This picture, I want you to think of limits not just from the right and the left, but from every possible direction. Another thing, if you're not thinking about mountains, you can think of a room. You're sitting in a room, it has 3 dimensions now, and there's a temperature value at each point in the room. And so you can come from all different directions, not just north, south, east, west, but you can come from all directions in 3 space, and it still has to be continuous. So there's nothing special about directions just being right and left. It really depends on the space you're living in, and you have to be able to approach from any direction, and the limit has to be equal from any direction in order for the limit itself to exist. So the idea of right and left is already wrapped into this definition, the limit as x approaches a. This means right, left in 1 dimension, and it means north, south, east, west, etc. in 2 dimensions, and in 3 dimensions, from anywhere, really. All of them mean from anywhere. Okay, I hope I haven't belabored that point too much. Okay, we have another common snag in calculus. So just to be clear about limits, I want you to consider this example. What does this equal? I'm just going to rewrite it. Okay, so the absolute value of x, and this is just, a real value in here. It's just 1 dimension, real value. This is equal to 1 when x is positive, and it's equal to -1 when x is negative. And it does not exist if x equals to 0. Okay? But we also have a function signum of x, which is different. We call signum of x is very, very similar. Okay, so this function looks like this. Let's see, we have a hole. It's got a jump discontinuity in it. And the only difference between absolute value of x over x and signum is that signum throws a point right in there. So it still has a jump discontinuity. It just is actually defined at 0. Okay. What else? Okay. So in both of these functions, I'm going to call this g. Okay. So I'm going to say limit as x approaches 0 from the left of f of x equals limit as x approaches 0 from the left of g of x, which is equal to -1. So this little negative sign, it's not -0, it means from the left. Okay? And I can do the same thing, but make it from the right, and then I'm going to get +1. Okay, so I'm going to just copy this out. There we go. So this is going to be from the right. I'm going to just change this to a plus. Alright, so it's going to be from the right. And then it's going to be coming from this direction. It means it's going to the value +1. So if the limits from the right and the left disagree, the limit itself does not agree. But if the limits from all directions agree, then the limit itself exists. Okay, so what can we do with these limits from the right and the left? They actually do have a good use, and you may not even have to write it down, but in your head you're thinking about it. They help you with graphing asymptotes, so you get the direction of the asymptote right. You want to know if it's a positive infinity asymptote or a negative. Very often we have one is positive and one is negative, and they're paired on the same asymptote, so you want to know which one is which. And so, for example, let's say I have to plot this function. Now, I'm going to be sneaky here, and I'm going to just factor this guy out. And I happen to know that I have 2 copies of x minus 2 in the denominator. So I kind of can cancel these guys out as long as x does not equal to 2. But I already have an asymptote there anyway, so I'm not going to have an additional problem. I already had a problem there. So it doesn't much matter, does it? Okay. In other words, not like before where we had an asymptote and a little point discontinuity, like a missing point. Alright, so this, okay. I'm going to show you a little bit of algebra. A lot of people, I've never learned this algebra, so I'm going to teach it to you. I'm going to add and subtract 2 to the numerator of this fraction, which means I did absolutely nothing. But that allows me to do this little stunt. So I can pull out the 1 and then write 2 over, x minus 2. So, yeah, that's one of those things that somehow gets forgotten in high school. I mean, they didn't teach me in high school either, so I don't feel bad. Alright, so, and that was a while ago. So, let's see. This is, you're shifting, there's an asymptote at 2, right? And there's another asymptote at 1. I probably need to do a little quick review on plotting rational functions, don't I? Well, this is part of it. So I'm thinking about the function 1 over x, and this is a shift of that. So first I'm going to shift it over, and I'm going to stretch it, which I don't really have to draw, but I'm going to lift it, which I do have to draw. And so, so this is at 2, and so I'm going to have, it's just going to be the same shape as 1 over x. And let's see, at 0, it's going to be 0. So it's going to look something like this. There we go. But let's say I didn't know that this was just 1 over x that was being shifted. Okay? But we haven't officially, do we officially do that? I don't know. Maybe that's my 170 class. But you should know how to shift these graphs around. But let's say you didn't. Let's say you simply knew that there was some kind of asymptote and you wanted to know if it was going positive or negative infinity. You could say, well, I would like to take the limit of f of x as x approaches 2 from the right. And in this case, I'll find out that it's going to infinity. And sometimes limits are paired, like 1 over, 1 over x squared looks like that, right? So sometimes those asymptotes both go in the same direction. So I want to test both of these. X approaches 2 from the left. I'm going to find out that that's negative infinity, and that's going to be this guy coming down here, and this is going to be this guy going up there. Okay, so let's do some numerics with this. Okay, so I just made up a little chart, and I'm saying I'm going to investigate the function at x equals 2, but at x equals 2 it doesn't exist. So I'm going to get close to 2 and see what happens. So if I just go a little hair over, I get 2001. And then that's just calculating it without canceling stuff out and doing anything funny. That's just what it is. If you just plug that in, it just is. And then these guys do this crazy thing. I mean, you can see what's happening. You're essentially getting rid of the decimal point and putting in a negative for these lower. So these are from the left, and these guys are from the right. And it's pretty clear if you play with this, the limit as you go to x goes to 2 from the right is going to infinity. And this is really abbreviating here because I didn't even put f of x, but limit as x approaches 2 from the left is negative infinity. Okay, let's say you don't want to calculate that by hand and it's a homework exercise. So you go to Wolfram Alpha. I mean, you could pull out a graphing calculator, sure, but why bother? You're sitting at a computer anyway, right? So let's say we want to know x squared minus 2x over x squared minus 4x plus 4, where x equals, I don't know, 2.00001, and it will just tell you. And but it's still there, so you don't have to even type it in again. Well, I don't really like that. Something got typed in wrong. I don't know. That's better. See, Wolfram Alpha was acting flaky on me. That's the kind of result I want. So what happens if I say 1.9? What happens? It tells you it's negative 19. Well, what about 1.99? Sounds good. Let's see how long it takes before it goes flaky on me. So that one's okay. That's definitely going to negative infinity. But 2.0000001, let's see what this one does. Oh, it's okay. See, it's right down here. Yeah, it's good. I don't know why it's not plotting it for me. But, so you can even just feed in a whole bunch of values all at once, but I'm not going to go into that. This thing is really powerful, and the nice thing is it takes input directly from your keyboard, which your graphing calculator doesn't do. So anyway, for a homework tool, I don't think you can beat it. It will debug your homework for you very nicely. Okay, and with that, I will leave you with that thought, and see you very soon. Have a good evening.